Oh, thank you, Juan, for the very nice introduction. I would like to thank the organizers for their excellent service to the community by organizing such a online seminar, especially during the pandemic where nobody can travel. And I'm really grateful that I have the opportunity to speak here. So today I'd like to talk about some recent results on the vortex symmetrization problem for the 2D Euler equation. Actually, the MAM problem is still open, so it's so if you're interested, there's still like a major prize to catch. This is based on joint work with Alex Ionescu. So feel free to unmute and ask me any questions you have during the talk. So we know that, of course, real fluid flows are three-dimensional, but in many cases, for example, in the large scale flows in oceans and atmosphere, some structure, especially the structural behavior of the fluid, can be viewed as two-dimensional. So the study of two-dimensional fluid flows is also like physically relevant. And in addition, they are extremely interesting mathematically. So these two-dimensional flows are often dominated by like a large vortex or group of interacting vortices. So we want to understand the dynamics of these vortices. So to do this, we study the two-dimensional Euler equation now written in this vorticity formulation. So you have omega is a vorticity field and U, which is a velocity field. The equation is written as partial T omega plus U dot gradient omega is equal to 0. So this is a transport equation of the vorticity field where with the velocity field determined through the vorticity field by this Biot-Savart law. So you firstly solve the Laplace equation to get the stream function, and then you take the perpendicular gradient to get the velocity field. So this is kind of a nonlinear transport type equation. For this equation, actually, I mean, it's 2D, okay, it's not 3D, it's 2D. For the 2D Euler equation, we know that smooth solutions remain smooth and exist globally for all times. So the regularity is not like the central problem here. But the long-time behavior of smooth solutions is, however, very hard to understand because we don't have any global relaxation mechanism. So just from this equation, one would not expect, a regular behavior because you have this nonlinear transportation equation. It's just the velocity field transports your vorticity as a scalar everywhere. And it doesn't seem, you have any kind of relaxation mechanism in play. However, remarkably, in both numerical simulations and in actually physical experiments, one often observes two striking processes for this 2D Euler equation. The first is axis symmetrization of vortices. If you put I will talk about what is a vortex, but you have this steady state, which is then you perturb it, somehow it will return to another steady state, which is radially distributed vorticity. And also, if the two vortices are of the same sign and then they get close by like the external velocity field, then they could merge together to form a larger vortex. So these two processes are very important for the global dynamics of two-dimensional fluid equations. And today we are going to talk about the mechanism for the first one, axis symmetrization. So the second one is mathematically very challenging because it's a fully nonlinear process, and we have a very limited, almost no understanding mathematically about this process. So this is like a numerical simulation due to Theodore Drivas. So here on the left, you have some initial distribution of vorticity, and you can see, so these are like the round blobs are the vortices. And you can see that the dynamics of the 2D Euler equation simplify the global picture or the global distribution of vorticity. You see that the number of vortices decrease, and then you in the end, you will only have like two left. So you see that if the big vortex is moving under the influence of external velocity field, but then it could symmetrize the small like noise around it. And then if two vortices get close to each other, they could also merge. So you have these two simplifying feature, essentially both due to the dynamics around the vortices. So this shows, I think this just tells me that the study of vortex is a central problem for the 2D Euler equation. So in this talk, we just study the stability. I mean, this is a starting point, the kind of the first step in understanding the global dynamic picture for 2D Euler. We want to study the asymptotic stability of vortices because it's kind of, it is a mechanism that somehow simplifies the dynamics. So, I mean, stability problems in fluid equations are a very classical problem. It's been studied ever since PDEs was written. So, for example, by Kelvin, Rayleigh, or Helmholtz, among many others. And we also have many recent works by many people. Here, for example, let me just highlight a paper by Weijiang Zhao, who obtained the first kind of comprehensive stability result for the, I mean, on the linearized flow around shear flows. And also recently we have many deep results about nonlinear asymptotic stability. So for the starting point is a remarkable paper by Bedrosian and Mahmoudi on coed flow on T times R. So this is a paper which kind of kickstart everything, and many ideas introduced here also essential for all subsequent works in this area. And also the work with Alex on the channels, on the finite channel. So the work by Bedrosian and Mahmoudi is on the whole space. We are on the channel. And also more recently, we had result on general shear flows. So these are all shear, and also independently by Mahmoudi Zhao, these are about the shear flows. So today we're going to talk about the asymptotic stability problem for vortices. So this is a kind of a more natural problem from the physical point of view, because here, for instance, the domain has to be T times R. So in the X direction, we have to assume it's periodic. But in the, so it's kind of, there's like a small kind of condition that there, which is not completely desirable. But for the vortex problem, all the undesirable features disappear, because here theta is a natural variable in the polar coordinate, theta r are the natural variables, and theta is automatically periodic. So everything is very natural in the vortex problem. So what is our central problem here? So the central problem can be formulated, roughly speaking, as the following conjecture. So if you take any radial function, so this is automatically, any radial function as a vorticity is automatically a steady state for the Euler equation. So let's take this radial function as a background vorticity field. Let's assume it's smooth as you like, even analytic, doesn't really matter. And it has, oops, sorry. It has fast decay. Okay, usually, okay, fast decay it could mean compactly supported. It doesn't really, I would not worry about that either. So, but it's kind of a natural, right? So you don't want to create a problem by assuming something is non-smooth. So everything is smooth and decays fast. So this background flow is very nice. And then you consider like a small, some initial vorticity field, which is close to this radial vorticity. So omega naught is close to omega, capital omega, in some topology which could be as strong as you like. Okay, Jevry space, for instance, infinite smooth category, topology category. And then we want to say that the solution starting with this initiator to the 2D Euler equation asymptotically symmetrized as t goes to infinity. So what does it mean to be symmetrized? So more precisely, we want to say that this vorticity field, as time goes to infinity, converges weakly but not strongly to a nearby smooth vortex. So omega star. So this omega star. So the convergence is only weak. So the process of stabilization is a kind of violent process. It's not a very smooth convergence. It's a rough convergence. But the target, in the end, the limiting vortex is smooth and radial with respect to a possibly perturbed center. So this is the kind of the ultimate theorem we want to prove in this research program. Okay. So this is still, it's still a conjecture, right? So it's a conjecture, so it's the open problem. And the only available results are two types. Firstly, we have by now, I think we have a really good understanding of the linearized flow. Firstly, the results by Bezoshin, Zalati, and Vicor. And then recently, Alex and I had a result on this, and we'll explain what are the differences between the work. But I think we have pretty good understanding of the linearized flow. And also on the nonlinear, in the nonlinear results, so for the full nonlinear problem, we have vortex symmetrization near a point vortex. So it's kind of a special, with a special omega. So this omega is a kind of Dirac mass. So it's kind of not really in this category, but it's a kind of first result that shows this kind of result can be proved mathematically. So let's firstly consider the nonlinear problem, which is about the symmetrization around the point vortex, because this is a fully nonlinear result, and the spaces and techniques we use basically decide, it determines the right linear theory we need to develop in order to solve the nonlinear problem. Because so you can develop all kinds of linear theory, but the one that's correct should be the one that you can use for the nonlinear problem. So let's consider this point vortex case. So in this case, the background, the flow is given by a Dirac mass centered at a moving point PT with some strength kappa, and then plus a smooth perturbation. So this is our basic setup. Then just plug in this to the Euler equation. We see that this perturbation omega and the associated velocity field u satisfy the following equation. So you have partial omega plus, this is a velocity field generated by the Dirac mass, right? Because it's also centered, this is also centered at the PT. So this is a velocity field generated by the background background vorticity field, which is Dirac mass, dot gradient omega. So that transports omega plus the original nonlinearity. So this is the equation for the perturbed vorticity. And then the U is given again by the Biot-Savart law. And moreover, the point PT will also move because you have external, you have perturbation vorticity, which is not radial. So it will generate a non-zero velocity that moves PT. So PT moves according to this equation. So this is kind of a closed equation for the perturbation omega and U. For this problem, we need to assume that the point vortex is located outside the support of the vorticity field. This is very important because I think, as far as I know, that even when when you have a Dirac mass type of singularity for 2D Euler, and then the vorticity, general vorticity field, somehow the Dirac mass is located in the support of the general vorticity field, then even the local well-posedness could be a small issue. Not a small issue, could be an issue. But this support condition is preserved dynamically by the flow, so it's not a big problem for us. So the main result we obtained was the following: to assume that the initial vorticity perturbation is very smooth and small. Okay, so it's small because we have perturbation result. It's small. But also it's extremely smooth. In fact, here you see that it's a Jeffrey-2 regular. You have here the weight in this is a Fourier transform in XY. Okay, omega not theta. It's a Fourier transform in XY. It carries this exponential type weight, except that the exponent is 1/2. If the exponent is like 1, then you would have analytic norm. If this weight is polynomial in sine eta, you would have Sobolev norm. So this Jeffrey norm is kind of in between the Sobolev space and analytic spaces. So at the beginning, I feel uncomfortable with Jeffrey space because you have such a big weight. But now I really fall in love with this kind of space because it has the advantage of both worlds, right? You have you can control infinite many derivatives, but you still have the flexibility as if you are working with Sobolev spaces. So this is really analytically very convenient space. Suppose the initial perturbation is like this, then there's a smooth, unique global solution for the system of the perturbed system of the Euler equation, and this point always stays outside of support for the perturbation vorticity field. Moreover, this point will stabilize to a kind of limiting point very fast as t goes to infinity, and the vorticity field will symmetrize around this point, p infinity. So omega t will converge weakly to this function omega infinity, which is radial with respect to p infinity. So this basically is exactly the picture predicted in the vortex symmetrization conjecture. You have a point with as the background the vorticity field, and then you perturb it using a very smooth, compact supported vorticity field. And then this point will move, but they will move very, very by only like tiny distance. It will converge extremely fast, and the perturbation vorticity field will just symmetrize around the final point. Again, I think a striking feature of such result is that the convergence is violent, right? The convergence is only in weak topology, but the limiting function is very smooth. So that's kind of interesting. So I have a few remarks. So again, the first one I already talked about a little bit. So this is the special case of the vortex symmetrization conjecture. And also we need the Geoffroy-2 regularity on the initial data, and this is kind of necessary if we want to have the precise control we obtained in the paper. And this has been demonstrated by Deng and Masmoudi. And also, I mean, Deng Masmoudi, they show that even if you just perturb in a like not Geoffroy-2, just slightly worse than Geoffroy-2, logarithmically corrected Geoffroy-2, you already cannot expect such results in the context of co-ed flow. And our setting is a little more complicated than co-ed flow, so we fully expect such result would extend to our setting as well. And we also have the result by Lin and Zheng, which show that if you perturb in a much rougher space, like Sobolev space with low regularity, then even the linearized problem can have issues and you cannot expect such results. And also the fast decay of this point, the point where the Dirac mass is located is extremely important because this point, because in the end, we will center everything with respect to this point. This point is really the center of our coordinate system. But because this point moves, so that induces a global change of coordinate. And this global change of coordinate is very serious and causes a serious loss of regularity. And that's only compensated because this guy stabilized extremely fast. Okay, so let me just very briefly explain the basic mechanism behind such a convergence. So to see the mechanism, we need to work in the polar coordinates centered around this moving center PT. So therefore, let's just write our coordinate function coordinates xy as pt plus r cosine theta sine theta. So you see that we now shift from xy to r theta. So in r theta coordinate, we can write all the functions in this new coordinate. So for example, we set omega prime as omega in the new coordinate, the stream function also as psi prime, and then similarly for the velocity field. And then we can write down our equation in this new coordinate system. In the new coordinate system, we have this closed system of equations. So you see that omega prime is still satisfies this transportation equation, but it's just a little more complicated because we write everything in the polar coordinate. Oops, sorry. And also you have the stream function and then the motion of the point. So in this equation, the man term is the linear terms. So we have two linear terms in the equation for the vorticity field, which is pi t omega prime and kappa over 2 pi r squared partial theta omega prime. So all the other terms are nonlinear, and we have to somehow control them. But the expectation is that the linear terms will dominate. So let's firstly look at the linear problem, because all the stabilizing mechanism comes from the linear equation. So the linear equation is just this, and this equation can be solved explicitly, and we have the solution formula here. And from this formula, we have two important message, I think. So the first one is that this vorticity field, we cannot expect the vorticity field to be uniformly smooth. Because if you take derivative in R here, and you see that even if you assume the initial data here to be completely smooth, the solution will not be completely uniformly smooth. Because if you take derivative in R, you see that there's a T popping up. So you take more derivative, you have more T coming popping up. So you see that in general, we would expect the Sobolev norms to grow polynomially in time, and Jeffrey norms to or analytic norms to grow exponentially over time. But on the other hand, we can normalize this. So this is the fact it loses regularity is just due to a very specific type. So for instance, if you take Fourier transform in theta, and we see that if we modulate this function by multiplying a different oscillatory factor, and we can get this profile. And this profile will be, it's basically like you shift the coordinate system. And in the Fourier space in theta, it corresponds to multiply oscillatory factor. So then we have a very good picture about the linearized flow. So in the Fourier picture, the linearized flow is basically a very smooth profile multiplied with this explicit oscillatory factor. I think in the chat I have something. In the exponent.
The definition before this, with the definition of the class of functions. Before this, in the definition of class of functions, yes, there's a 1/2. This is real. It's not real. Scalar product is the power 1/2.
Yeah, this is the Jeffrey 2 space. So this is kind of the regularity class we need.
That's not the scalar product between C and eta, is it? It's just
oh, sorry. Yeah. Okay. So yeah. Thanks, Andrea, for the it's not the inner product. It's basically it's a Japanese bracket. I should have explained this. So this bracket alpha means 1 plus alpha squared to square root.
Wow.
Take a square root. Sorry,
Thank you.
This is not inner product.
Thank you.
Sorry, I think I just used the Japanese bracket so many times I forgot to explain what it is.
so do I, Hao.
Sure. Okay. So these are the kind of the my message that we have. We can have this smooth profile that we can control despite the fact that the vorticity field in general cannot be controlled in smooth norms. And also the decay can also be viewed here because we have the explicit formula for the vorticity field. The stream function is recovered from the vorticity field by integrating against the Green's function. And then you see that because the vorticity field actually carries this oscillatory factor, now you have this oscillatory integral. Then if you integrate by parts twice in row, then you get the quadratic type decay for the stream function. In general, we cannot get more than quadratic decay for the stream function because the Green's function here you are integrating against is not smooth, right? Green's function carries a singularity because two derivatives will give you a Dirac mass. So in general, you can only integrate by parts twice before you hit something that's not an integral. Okay, so that explains the decay of the stream function, and which drive the decay of stream function also gives you the decay for the velocity field, which drives the convergence of the whole system. So this is the linear analysis. In this case, the linear analysis is very simple because it can be solved explicitly in a very simple formula. But to extend to the nonlinear problem turned out to be very challenging. And but this part, I think we have already many talks about this, and they are basically many of the talks are actually online on YouTube or other places. So I'll be very brief about the nonlinear analysis here. So the first idea in extending from the linear analysis to nonlinear analysis is to make a changing variable, because we know that in the original variable the vorticity field is not uniformly smooth. So we want to remedy that issue. So one possible way to do that is to rename your coordinate system. You introduce this new coordinate system, which basically, I mean, the reason why you lose regularity over time for the vorticity field is because that you have this transportation effect. And now this new changing variable simply undoes all this transportation, and then in the new coordinate system we can get if we write our velocity field, stream function, and so on in the new coordinate system, we can expect that we will have uniform control for those functions. Now, if we write everything in the new coordinate system, which is we denote as z and v, so let's for example consider the vorticity function. Let's denote the new function as f. So this is the vorticity function in the new coordinate f. Then the f will satisfy an equation which is also which is also a transportation equation, but in the variable z and v. So let's not write down the full equation, but rather look at this model problem. Okay, this is a model equation. We have partial tf minus partial v of phi, where phi is phi solve this kind of elliptic equation. You have this variable because of the changing variable. So this equation is actually a closed equation. I think this is the best model one can have to understand the nonlinear stability result. So what is the main difficulty here? So you have transportation equation, and this equation implies, oh sorry, there's a phi missing here. So this equation implies that phi will decay quadratically over time. So at least in principle, we expect that the velocity field here, which transport f, will have very, very small effect because it has quadratic in time kind of decay, 1 over t squared decay. So the total transportation induced by this velocity field over all time will be very, very small. So the full effect of this evolution equation on this f would be a small, like a tiny change of coordinate for the initial data. So that's kind of the global picture. But there's a very serious technical difficulty here, because if we take a Fourier transform in this equation, we'll see that the velocity field here is given explicitly with this formula. But the danger is so you have the psi over k squared. So basically, in this velocity field, you have partial v. Okay, you have partial v here on phi. So this partial v has to be recovered from somewhere. So it has to be recovered from this elliptic equation. But you see that in the elliptic equation, you do not really recover partial v. You recover partial v minus t partial z. So there's a mismatch between the loss of derivative and the recovered derivative. So in reflecting the Fourier space, we can see that you have this psi divided by t minus psi over k. So this factor is potentially extremely large if psi is huge and the k is not huge. So that's the so-called resonance problem. And to deal with this issue is quite non-trivial. And in fact, in the end, we can close the estimates and prove smooth control on f by controlling time-dependent energy functional defined like this, associated with some time-dependent and imbalanced weights. But the price we pay is that the energy functional we use has to be decreasing over time. So basically, this ET give you less and less control over time. So you have to lose your energy control even when f is stationary. Okay, even when f is stationary, this guy will automatically decrease. That's designed in a very specific way to cancel this kind of large factor. This actually requires a very considerable effort, and the first idea was introduced by Zhou and Masmoudi, and it has been used in all subsequent works, as I mentioned earlier. So that's but in the end, the analysis is not subtle. Okay, it's because everything is measured by its absolute value. So you can take, after you make a Fourier transform, everything can be measured in absolute value. No cancellation will be needed in a way. So it's just about the size. So in that way, it's not really too delicate. But that's for the co-ed flow case, we already have all these difficulties. But in our case, we have some additional difficulty associated with the global coordinate shift and the presence of variable coefficients. Basically, because PT will move, so that introduces a global shift of a coordinate system, and that naturally is associated with some function of this type. You have P prime T cosine theta, right? PT moves. So cosine theta is a smooth function in the r theta coordinate. So that's associated with transportation in x. So this function in the r theta variable would be very nice. But we are working with z and v variable, but theta is given by z plus tv. So suddenly we are looking at p prime t cosine z plus tv. And this function cosine z plus tv is horrible because it carries a tv here, and then if you take derivative in v, you have polynomial growth in the derivative. So in fact, because we work in Jeffrey space, the Jeffrey norm of this function grows almost exponentially. And that's only compensated if we want to control the unit in Jeffrey space uniformly. That's only compensated by the very fast decay of p prime. So everything in the end remarkably exactly match. We have exactly the same kind of decay to compensate this precise loss of regularity. And also we have the variable coefficients. In the end, we have to use some commutative estimates and some refined weights. This I will not discuss in detail here. So instead, I will actually now move to the general problem, which is the vortex symmetrization problem for general radially decreasing vortex for the 2D Euler. So in this case, let's assume, so in this case, the general nonlinear problem is still open. Okay, we now have, what we have been doing is to develop a linear theory which is robust enough that we have hope to match the nonlinear analysis. So to summarize the state of affairs, so basically we now matched the regularity requirement. So we can control the linearized flow precisely enough that we end up in the same regularity space required for the nonlinear analysis. But still, there's a significant difficulty we haven't been able to overcome. So I'll try to explain in the rest of the talk. I'll try to explain what these difficulties are. So let's consider this velocity field, vorticity field given by omega r, which is decreasing and smooth in r, and its associated velocity field ur e theta. So omega r will generate this rotation, but it's very important that this rotation is not rigid rotation. It's a differential rotation. If you have rigid rotation, you will not have symmetrization. It's because so it's only because this is a differential rotation, namely that the angular velocity introduced by this velocity field depends on r. So that's why we can have this. It's a very important feature for symmetrization. Now, by Biot-Savart law, there's a relation between u and omega given by this formula. And then the linearized two-dimensional Euler equation can be written as follows. Basically, you have the same kind of nonlinearity, but the linearized equation becomes a little different. So we don't have the PT anymore, right? There's no center that we really have to focus on. So we now have this kind of linearized problem. And also string function can be written as, or can be determined by the vorticity field through Biot-Savart law. Now, in comparison with the point vortex case, a very significant difficulty is this additional non-local term. Okay, this is also linear term. In the point vortex case, we only have a transportation equation on the linearized level. But for the general vortex problem, we have this non-local term. This non-local term introduces a significant difficulty. But also for the general vortex problem, another significant difficulty is that now we have no right to assume that omega to be supported away from the center. So omega, so what perturbation vorticity has to be assumed to be everywhere. So the support will touch the center of the vortex. So in particular, omega is supported not away from r equal to 0. It has, the support will touch r equal to 0. Even if we assume initially it's supported away from the center, this term will make it non-zero almost everywhere. So somehow the analysis of the center is now extremely important. So basically, in comparison with the point vortex case, we have two additional difficulties. One is the linearized problem has this non-local term. As we shall see, this non-local term cannot be treated perturbatively. And also, we have to analyze the behavior near the center, where there's a very serious degeneracy. So basically, I think we can say that we now understand how to analyze this term, but not so thoroughly about this term in conjunction with a nonlinear analysis. If you're just happy with the linear results, we could say, oh, we almost understand everything. But if you want to develop a linear theory that's well prepared for the nonlinear theory, I think we still have some work to do. Okay, so because of this non-local term, we can no longer solve the linearized problem explicitly. Instead, we need some spectral analysis. And in fact, this kind of non-local term already appeared even when we consider the simpler shear flow case. The shear flow is like a parallel flow given by by 0 on some domain. So in comparison with the co-ed flow, basically because B double prime, so for co-ed flow case, B double prime is equal to 0. So you don't have the non-local term, but here B double prime is not 0 and you have a non-local term. Oh, sorry, maybe I should, there's a question on the chat. What is C prime and omega prime? Do you mean here or previously? I think previously I also have here,
no,
right?
Just in 13 and 13 formula, this right red formula, this one, yes, this red term, what is psi prime?
Oh, good questions. Sorry, I think I pasted from the point vortex case. There shouldn't be, you're right, so there shouldn't be a prime here. It's just psi and omega.
Okay, thank you.
Thank you. Thank you very much for the correction, because I think I just copied it from my point vortex slide, and but I should have made some changes. Okay, so this non-local term already appeared for the shear flow case, but in that situation, we were able to handle it basically by firstly trying to understand the linearized flow using very precise spectral analysis. And also for the nonlinear problem, we were able to define a modified profile because of this non-local linear, you have this additional linear term. So the flow, the vorticity will no longer evolve completely perturbatively. Actually, the dominating, in terms of size at least, the dominating evolution is a linear evolution. The nonlinear evolution should be viewed as a small correction, rough but very tiny correction. So we were able to define this modified profile, which evolves perturbatively according to nonlinearity. And then the full profile can be recovered from this modified profile by spectral analysis. So this was done by Alex and I, and also independently by Massimo Rizzo using a different method. So in the shear flow case, basically the message is that there's a significant difficulty due to the appearance at the linear level of a non-local term, but we were able to overcome them. And my message is that there's still a smooth profile. So you have the loss of regularity on the vorticity level, but you are able to make a change of coordinate and get this smooth profile and work with smooth profile and get the nonlinear analysis done. So how about in our situation? Can we do the same? So that's the question, right? So let's analyze the linear flow in more detail. So for the linearized flow, let's take, if we look at here. So forget about nonlinearity, take the Fourier transform in theta. I mean, a very significant simplification for all this linearized flow is that you have the separation variables. So the coefficient here is variable coefficient, but it doesn't depend on theta. So you can take a Fourier transform and transform this equation into a family of decoupled simpler equations. So we take a Fourier transform in theta, and the Fourier mode is indexed by k. So we have this kind of a family of equations for omega k. So we want to understand this equation as thoroughly as possible. So as in the case of a point vortex problem or shear flow case, naively one might hope to get this profile by canceling this oscillation, because right, if you look at this equation, ignore this term for a moment because this psi k is smoother, at least in principle it's smoother, so probably less important. So let's just focus on this term, and then this term will introduce oscillation. So let's remove that oscillation and hope that this one will be smooth uniformly for all times. That's what we got for the point vortex case and also for general shear flow case. That's a natural thing to try. But it turned out, so this was attempted in a work of very significant work by Zoshin, Kodizalati, and Recall, who proved that this FK defined like this will have some regularity. It has some limited regularity depending on K in Sobolev spaces. So for a while, it's not clear if it's a technical issue or a general real difficulty that one cannot do it for infinite smooth space to have a smooth control on FK, because that's what is required for nonlinear analysis. For nonlinear analysis, we require Gevrey space. So to reach Gevrey regularity for the linear analysis is kind of a milestone. But this turned out to be impossible. We cannot, in general, we cannot control FK in a smooth node. This is due to the degeneracy of this oscillatory factor UR over R. Actually, because UR is coupled with E theta, right? So UR E theta. So UR has expansion as R go to 0 in the form of R plus R cubed. So if you divide by R, take derivative, naturally this is equal to 0. So that means your oscillatory factor has a degeneracy. This degeneracy is for now is responsible for all the remaining difficulty we have in extending to nonlinear problem. So instead, we should abandon this kind of decomposition. We should decompose in a more complicated way as follows. So we should have two profiles, F1K and F2K. So F1K is basically as before. You have this guy carries oscillatory factor, and then F2K, which is already smooth and no longer carries any oscillatory factor. So moreover, these two profiles are uniformly smooth over all time in Gevrey space. So we basically have very good control on them. So now if we compare this result with the result of B, C, and V, the reason why we can only get limited control in their very significant work is kind of clear, because if you define the profile in somewhat unnatural fashion like this, I mean, apparently natural, but ultimately incorrect fashion like this, you see that this guy, it's very good for this term because you cancel the oscillatory factor, but for this term, it's not so good because you artificially introduced another oscillatory factor, and that oscillatory factor has a derivative which grows in time. The only reason why they were still able, somehow almost miraculously, they were still able to get like the sharp limited regularity in time, in space over all time, is because this guy actually has some decay over time, but the decay is not infinite. Okay, the decay is algebraic in T, so you can depending on K, so you can get so much control if you introduce this artificial kind of oscillatory factor. So that's the main result we obtained with Alex. So let me try in the remaining 10 minutes or so, let me try to explain what is the basic idea here, because as I mentioned earlier, the significant difficulty here is that this term is no longer perturbative. Actually, it's dynamically very important. So because this problem cannot be solved explicitly, so naturally we have to carry out a spectral analysis. So we just write down the standard spectral repetition formula in terms of the spectral density function associated with the problem. So the spectral density function satisfies an equation associated with the initial data. So this is the equation the spectral density function satisfies. So this is kind of completely standard at this step. But this equation actually is quite non-trivial because the spectral formula we get is obtained by collapsing the spectral parameter into the continuous spectrum, because you are dealing with a parameter. So here basically written by BR naught plus I epsilon. So that spectral parameter collapses to continuous spectrum. So you are getting close to continuous spectrum. You expect certain singularity. And the singularity is revealed here where you have BR minus BR naught. So R could be R naught. So that shows you have a singularity in the spectral density function, which is completely expected. So this guy is not smooth when R is equal to R naught. So it turned out that because this equation contains variable in the leading order, contains this variable coefficient, it is actually more convenient to work with the variable V, which is log R. So now we switch all the variables into the V variable from R variable. and write down the spectral density function in the new coordinate system, and also the background flow in the new coordinate system, the initial data also in the new coordinate system, and so on. And then we obtain a new system, okay, new equation for the spectral density function. And then in the new equation, the stream function can also be written as again by this spectral density, the integral of the spectral density function. So basically, then you see that everything, I mean, it's expected that when you analyze such a linear problem, everything is reduced to understanding the spectral density function. Now, for example, if we want to control, to get a quadratic in time decay of the stream function, we just have to take a derivative integration by parts twice in this formula in W, right, with respect to spectral parameter. If we can integrate, so basically we have to understand the behavior of two derivatives in W of this formula. So again, because of it's a linear problem, everything can be reduced to the study of a spectral density function. And the spectral density function satisfies this nice equation. Now, so the question is, what kind of behavior can we expect for the spectral density function? So if we look at this equation, you see that we cannot expect the spectral density function to be smooth, to be completely smooth. In fact, it always have a singularity, because when V is equal to W, the equation contains a singularity. When your equation contains a singularity, you cannot expect unless a miracle happens, you cannot expect your solution to be completely smooth. So indeed, this equation, the solution has a singularity when V is equal to W. But so that's not a good object, because we always want a smooth object. We don't like non-smooth object. But so what do you do if you have a singularity? When you really like to have a smooth object? So the alternative would be to completely characterize the structure of singularity. So in this problem, it is very simple to do that. Basically, we make this changing variable. Instead of looking at the VW, now we look at the variable in V plus W. So what is the advantage of that? So, well, if we shift V to V plus W, so then the singularity is transformed from BV plus W minus BW, which is no longer singular in W. So this shift of coordinate basically shift all singularity from both V and W to only singularity in V. So that's the advantage. Basically, we expect this object to be completely smooth in W, but is singular in V. So that's exactly what we can prove. We can prove that this object, so the kind of the profile for the spectral density function, is very smooth in W and not so smooth in V. In fact, two derivative in V will have a singularity, Dirac type singularity at V equal to 0. But also, moreover, that this guy is actually very smooth in V if V stays away from 0. Basically, the only singularity is when V is equal to 0. If V is not 0, it's very smooth. In fact, it's much smoother than the initial data. It's basically the smoothness in V away from 0 is only determined by the background flow. And also because we work with V and W, which are log R and log R naught. So R and R naught are from 0 to infinity. So V and W are defined on the real line. So these are functions defined on R2, theta k is a function defined on R2, depending both on the physical spectral variable and the spectral variable. So we need also supplement the regularity estimates with suitable decay, and we do have this physical space decay. And we say that this function is not smooth in V when V is close to 0, but we have a remarkable characterization of the singularity structure. So basically, you take any smooth function zeta, you consider this expression, so zeta V plus rho minus zeta rho. So so this guy is not, so in this variable, it's not smooth, right? And when V is equal to 0. But if you take a transformation like this, then this is actually smooth in rho. So almost like in the singularity, this rho is cancelled. So this function is very smooth in rho and W. So that gives us a very nice characterization of the structure of the singularity when V is equal to 0. And also, of course, we have the representation formula for both the vorticity field and the stream function. Now, from that result, it's clear how we can define these two objects. Okay, we can define. Sorry, I think I'm missing this one oscillatory factor. So basically, you look at the representation formula in terms of spectral density function, and then you just cut off. You cut off when V is near W, where you have a singularity, and when V is not near W, where you do not have a singularity. For the second part, everything is already smooth. There's no need to introduce oscillatory factor. For the first part, when V is equal to W, you do have a singularity, right? When you have a singularity, you need to, so when you have oscillatory factor integrating against a function which has a singularity, then you pick up, right? After integrating, you pick up the oscillatory factor. So that's why you need to, for the first one, you need oscillatory factor. The second one is already smooth. So that gives you naturally these two profiles. Sorry, I think do I have 1 more minute?
Yes, please go ahead.
Oh, okay, thank you. So let me just, so moreover, from this formula, we can also have the enhanced decay. We can also capture, because we have the decay for theta k, we can also get the decay for the profiles. This decay is actually faster than the expected decay, and this so-called vortex depletion phenomena, and it was observed by Bouchian and Morita, and established rigorously by Weizhang Zhao in the shear flow case, and Bedrosian Kodizalati recall for vortices case. So our work is basically to give a kind of a more precise understanding in terms of regularity and in terms of profile for the linear problem in preparation for nonlinear analysis. So maybe I should take just 1 minute to briefly explain what is the idea here. So as I mentioned earlier, so the main thing is to analyze this equation. Okay, this is the equation we have to analyze. The main difficulty is this equation has singularity. Okay, first difficulty is it has singularity because when V is equal to W, this is singular. The second difficulty is that this potential term is not perturbative. Okay, this potential term is not perturbative because when there's a simple calculation, when W is very, very negative, this potential term is equal to 8. So on this very long interval. So when W is less than 0, but with a very big absolute value, then this potential term is equal to 8 on a very, very long interval. So basically, I mean, when we look at the linear problem, what do we look at? So we have a high frequency component, we have medium frequency component, and we have a low frequency component. Because now we are in the whole space, so all these three frequencies are active because it has a long physical dimension. So the right, you have a low frequency, and of course this is a differential operator. You also have a high frequency and a medium frequency. In this problem, the term here is not a problem for high frequency because we have certain compactness that the high frequency component is dealt with by regularity estimates. Medium frequency, that's the hardest part usually. The medium frequency is handled by spectral assumptions, right? When you have active medium frequency in your problem, you have to use spectral analysis. But in this problem, we also have a low frequency issue. And the low frequency issue is reflected in the fact that the potential is not decaying on a large interval. So instead of looking at this as a main term, we actually have to extract a part of the potential and incorporate it into the main term. And then from that, we can handle the rest of the problem. For the singularity, basically, we make the same shift to shift the singularity from both V and W to only singularity in V. And then we study the Green's function associated with this operator rather than with this operator. And then we can obtain, using limiting absorption principle, to obtain some estimates, preliminary estimates in Sobolev space, and then use commutative arguments to directly go from the low regularity estimates to infinite smooth estimates in whole space. Okay, sorry, I think I'm running out of time, so let me just stop here, and if you have questions, I'll be happy to answer them. Thank you.